Oh, drat. What's happened here? Oh, no, okay, it is recording. And it's getting audio. Okay, sorry about it. So we got a couple questions to go over. Most of it is kind of evenly split between how we think about gases and how we think about thermodynamics. And so we're going to work on both of those things. First, we're going to start with just the idea of how we talk about gases. So we're going to start with the gas stoic questions. And question number 1 from the stoic questions relates to kind of the report form and prep activity. Definitely number 6. Number 6 is essentially a repeat of the experiment with a different chemical reaction. But we'll start with number 1. We'll take a quick look at number 6, which relates to these things we're going to talk about later. And then we'll move into talking about thermodynamics through the middle. Calculate the moles of hydrogen gas produced by the reaction of 0.82 grams aluminum with hydrochloric acid. So we've got a certain amount of aluminum that we're going to react with hydrochloric acid. So we've got aluminum solid plus HCl. My guess is that this is going to produce AlCl3. Common charge of aluminum is +3. And H2 gas. Now, in order to get these 3 chlorines, I'm going to need a 3 here, but then I'm going to have an imbalance between my H's. So I'm going to need a 6 there, a 3 there, a 2 there, and a 2 there. Hey! Settle. Sorry about that. Glacier. Glacier's not supposed to bark. Okay, so this is our balanced chemical reaction. 2 aluminums for 6 HCl goes to 2 AlCl3 plus 3 H2. And we've got a specific amount of aluminum that we're going to react, 0.82 grams. And it doesn't say this in the problem, but in my opinion, they should say specifically with excess hydrochloric acid. We can assume that it's excess hydrochloric acid because they don't give us an amount, but really it should specifically say excess hydrochloric acid. We're going to find the number of moles of aluminum. So we want to find the hydrogen gas produced in moles. So we're just going to do some stoichiometry. I'm going to need the fact that 1 mole of aluminum has 26.98 grams of aluminum. That'll cancel out my grams, get my moles, and then it's just the mole ratio between the two, which is 3 moles H2 for every 1 mole aluminum. And that should very easily give us our moles of H2 gas produced. You'll notice the moles of aluminum cancels out, the grams of aluminum cancels out, and I just get moles of H2. If you incorrectly predicted the common oxidation state of aluminum or you didn't look it up, that can throw off the problem. Now, when we continue this, we could ask further questions about this, right? We could say, well, what volume of gas would be associated with this? And that would bring in the ideal gas law and everything like that. And we could keep going. But this is just really asking us to do the stoichiometry associated with it. So if we plug those numbers in, if you got something different than 0.82 grams, you probably did. You'll have to put your numbers in. But the idea is balanced chemical equation, stoichiometry. Right? And then once you've got that amount of gas in moles, then we can apply ideal gas law and things like that. Did that help out? I think this was Ashley's question. She might be watching the other video. Okay. So then the question becomes, well, how do we make it more complicated? How do we bring in these other ideas? And that's really getting to gas stoic question 6. If there are no other questions about this. Oh, you are so right. That would be a 2. Got carried away. It'd be a 3-to-2 ratio. Thank you for catching that. Great. Okay. So in question 6, what it does is it does a different chemical reaction. Right, question 6 is a bit more complicated. It's trying to recreate the experiment. And Jennifer, technically, no, you don't have to answer the questions worth 0 points. But you should try. You know, it gives you something to think about, kind of gets you the concepts behind what's going on. I think those should be worth points, but it's also the end of the quarter. So in this one, we've got an oxygen, we've got potassium chlorate reacting to form oxygen gas. They do the same thing and collect the gas, and it's asking us to figure out what the ideal gas constant is. So we can imagine, you know, when we look at our ideal gas law, we just look up what the ideal gas constant is. R is 0.08206, kind of, you know, we just know it. But that had to be experimentally determined. So the question becomes, well, what kind of experiment would determine this? And this is what it's kind of getting at. Actually, the experiment where we used magnesium to produce hydrogen gas also could have been used to experimentally determine the gas constant, because we can measure the pressure, the volume, we could measure the number of moles and the temperature, and we should be able to determine the gas constant. So that's what this is asking us to do, where we have to follow through the same process that the experiment we did has, right? So we're going to have this beaker with water. We're going to have our EUdometer inside there. There's going to be some height of water above the beaker. And so we have to take that into account for the hydrostatic pressure. We have to take into account the fact that we've got more than one gas up there, the fact that there's going to be different components providing pressure. So we have to take into account that water vapor up there. And we also have to have a good assumption about what the pressure is, right? So in this, it says, oh no, we forgot to measure the atmospheric pressure for the day. What is the atmospheric pressure for the day? If you did your lab calculation already, you hopefully saw that most days, even with this like 30 inches of water or 30 inches of mercury, we were still at 1.008 atmospheres. And it turns out, even though we can have slight variations in our pressure, we're always going to be at approximately 1 atmosphere. Not exactly, but approximately for our operating pressure. So we're going to use the same equation we did for lab, which is pressure of the atmosphere is going to be equal to the pressure from the H2 gas plus the pressure of the H2O liquid plus the pressure of the H2O gas. Sorry, not H2. In this case, it's going to be O2 gas because we're doing a different reaction. But we're still going to have this hydrostatic pressure and this water vapor pressure. So the thing that becomes important is making sure that we assume the atmospheric pressure correctly as 1 atmosphere, approximately 1 atmosphere, and then subtracting off the other 2 pressures. That's going to get us this pressure term, where we're going to need to use those equations from the background to subtract those 2 things off. And the reason we want to do that is because we want the pressure of just the O2 gas times volume equals moles of O2 gas times R times T, right? We want just the portion that's due to the oxygen when we do our calculation. So we want the pressure just due to the O2 gas, not the atmospheric pressure that includes these other things. So we have to use an equation from the background to do those 2 parts. And then we should be able to follow through just like we did our lab report. Sebastian, does that help out? Does that make sense for how you would approach that? I think you just had the problem of figuring out that you assume it's 1 atmosphere.
Yeah, that makes a lot of sense.
Cool, okay. So both of those problems really are getting at how much gas is produced and how we can measure how much gas is produced. And question 2 from Mastery Question Set 14 kind of continues with that idea and actually has us do a full ideal gas law calculation. So that's what we're going to look at next, is once we've got this amount of gas and this pressure of gas, how do we use that information to actually get at some numerical values that are useful? So question 2 says, assuming I'm reading the right one, yes. What is the volume occupied by a gas in a container for which there are 1.27 moles of ideal gas at negative 59.46 degrees Celsius and 749.16 torrs of pressure, right? And so this one is really kind of like any of the equations we've looked at this quarter, where we've got some equation. In this case, our equation is PV equals nRT. And then we say, okay, well, which things do I know, which things don't I know? And in this problem, we're told the number of moles, so we've got our N. We're told the temperature, it's a cold container. We're told the pressure, and of course, we know the gas constant. So the only thing we don't know is the volume in this case. So the part we have to be careful about in this one is unit analysis. So if we just went ahead and plugged in the numbers, 749.16 torr times volume equals 1.27 moles times 0.08206 liters, atmospheres, moles, Kelvin. Sorry, I didn't give myself enough space. Times negative 59.46. Right away we can see that there's some pretty serious problems if we just throw everything in. Torr and atmosphere are in different units. Celsius and Kelvin are in different units. And since Celsius can go negative, that's going to create a headache as well. So we have to do a couple different switches. First off, we have to do our torr to atmosphere. And then we also have to do our Celsius to Kelvin. And then we can just do the calculation, right? And this equation is actually quite fascinating and quite important. Since I've been teaching at Cal Poly, we always jump straight to the ideal gas law, but if you've taken chemistry class in high school, or if you went to a chemistry class in community college, or watched different videos about the ideal gas law, I think even the one from Bozeman Science we had you watch this week, talks about Boyle's law and Charles's law and like all these other scientists who discovered different bits of behavior that gases have. And the ideal gas law puts all of those behaviors together into one equation. So in this way, it kind of makes it a little bit more difficult to figure out what's going on. But I always like to think of isolated units, or isolated variables. So I look at how do pressure and volume relate if moles and temperature are constant? How does pressure and temperature relate if moles and volume are constant? And it turns out that there's this direct or indirect relationship between, or this direct or inverse relationship between all of them. But in terms of doing the calculation, as long as we're in the right units, we just plug it in and we go. Things that we have to be careful about for some of the other more complicated problems we have is this the pressure of one component or multiple components? And will that give us the moles of one component or multiple components? Which gases actually follow ideal behavior? Which gases do not follow ideal behavior, right? Ideal behavior has some certain considerations. I'll give you an example. Water vapor doesn't behave very ideally, right? One of the most important things for an ideal gas is that we have non-interacting gas particles, which means no IMFs. But we know water molecules, whether they're in the gas phase or liquid phase, have a pretty strong dipole moment, and you're going to have some dipole-dipole interactions. We can approximately neglect those, at reasonable temperatures, but that's important because if all gases actually behaved ideally, there would be no liquids anywhere. Liquids would not exist because liquids are essentially condensed gases because gas particles can't interact. But again, this is general chemistry. We're just going to assume ideal behavior for most of our gases. As we go on to master question 14, number 1, this one's interesting. Any other questions about this before I move on? And Ashley, I'll address your question in just a moment. Okay, so in question number 1 for Mastery Set 14, it essentially gives us this idea of you've got a balloon, it's full of a gas. The gas is going to behave ideally. And it kind of breaks it into multiple steps. It's like, first, what's just the volume of the balloon if it's a perfect sphere? And so that's just using the equation for a sphere to figure out the volume of the balloon and assume all of the stuff inside the balloon is the gas. And then it says if the gas is hydrogen gas, what's the mass of the balloon and the number of moles in the balloon? So that's just ideal gas law. It tells you 25 degrees Celsius. We get the volume from the previous problem. And then you just have to solve for n. Right, and that's fine. And this is an important step in the process because knowing how much gas there is essential for doing our stoichiometry, which is what happens next. So the next thing that we have is what's the enthalpy change when hydrogen is combusted, and then how much heat would be released if you set that balloon on fire and you combusted the balloon. And this is where I apologize that we're doing everything online. Usually I ignite a hydrogen balloon in class. We have to leave the building because it will break windows if you do it indoors, but I'll find a video and send it to all of you for a hydrogen balloon exploding. Or you can go watch videos of the Hindenburg. It's terrible. It's terrible. But we can start to think practically about energy release and amount reacting to get that energy release. So the first thing we have to remember is that the phrase hydrogen gas combusted is referring to a very particular chemical reaction. And combustion always refers to a very particular reacting with oxygen gas to produce CO2 gas and H2O. Oh wait, no, not in this case. To produce products, if we're combusting a hydrocarbon, we'll make CO2 and H2O, if we're being ideal. But in this case, where we're burning hydrogen gas, we just make H2O gas. To balance the chemical reaction, and get a 2 and a 2. So this is our balanced chemical reaction. Every mole of hydrogen gas we burn should produce 2 moles of water vapor. Again, there's nothing in this about how much oxygen gas is present, so we're going to assume that we have excess oxygen gas. And this says first, go ahead and calculate what the enthalpy of the reaction is if you just have 1 mole of hydrogen gas. So we can imagine, first off, let me check if I remember correctly. This is your question, Tabitha, and you had a couple questions with this enthalpy idea. How are you approaching calculating the enthalpy for the reactions?
Well, I used a different equation because it was the ethine it said is combusted for mine. Is that the same thing?
Oh, it might be different actually. This one might randomize what's inside the balloon.
Oh, okay, because mine says 1 mole of ethine, C2H2.
Okay. So we can look at it for that as well. Let's go ahead and do that one. That one's more interesting. I got a boring one in mind. So we're going to combust C2H2 plus O2. It's going to go to CO2 plus H2O. Always states of matter, or I'm going to take off points. And then balancing coefficients. Wait, C2H2? Ethine, yeah.
Yeah, C2H2.
Okay. Balancing coefficients. Oh, no, that's not right. Okay, we're going to need a 2 there to get my oxygens even, but now I've got 4 hydrogens, so I'm going to need a 2 there to get 4 hydrogens, which means I'm going to need a 4 here to get my 4 carbons, and then I've got 4 5O2s. Is this how you balanced it?
I did a couple different things because I couldn't figure it out, but initially I did 2 C2H2, 7 O2, 4 CO2, and 6 H2O.
You would have too many hydrogens if you did that, so that would be not balanced.
Okay.
So you might have just had some problems with balancing the chemical reaction. I'm pretty sure this one's right. I'm going to go ahead and double check it. I've got 4 carbons, 4 carbons, 4 hydrogens, 4 hydrogens, 10 oxygens, and it's going to be 4 times 2 is 8, 9, 10 oxygens. So this one is balanced.
Okay.
If you don't balance these correctly, you get nonsense for your answer. So that might have been the thing that threw you off. Now, how are you with the process of, once you have your balanced chemical reaction, calculating the energy associated, the delta H of reaction, or the energy released, or the energy associated with the reaction?
Well, like I said for MQ15, I get some of them right, but then some of them wrong. So it's, I don't know. Kind of
Okay, so let me go ahead and go through the process I always use, because and not to throw Dr. Neff under the bus, but it's really easy, especially if you're trying to do these quickly and in your head, to get the right thing. It's really easy to miss a bond someplace and not get the right count. Adriana, yes, we can go back to that in just a moment. I'll keep that in mind. So what I always like to do when I'm doing these problems is I actually like to draw the Lewis structures for everything I'm considering. So I do 2x, hydrogen to carbon, triple bond to carbon, hydrogen. I'm going to need 2 of those. I'm going to need 5x, oxygen double bonded to oxygen. And then I also consider my products, 4x and 2x. Right? And this way it's really obvious how many bonds I need to consider. I'm going to need, so when I do this, and I like to do it separately, products and reactants, so I'm just going to focus on the reactants first. I'm going to need 2x, 2 carbon hydrogen bonds plus 1 carbon triple bonded carbon. And I'm also going to need 5 oxygen double bonds. And there's just one of those for each, right? So this, I like to do it this way because I keep my balancing coefficients outside of the chemical compounds. For some people this is more confusing. For some people it actually works out really nicely and helps them organize a bit more. And then all I have to do is I have to get my equation sheet, and I have to look up my value for CH, and a CH is going to be 413 kilojoules per mole. So I'll just write this number in. Carbon-carbon triple bond is 839. And an oxygen-oxygen double bond is 498. So I can just do 2 times that plus 1 times that, and then I want 2 molecules of that for the C2H2, and then 5 times that for my O2. And that's going to be all of the energy. And this is going to be that's going to be a positive value because that's energy we're putting into break bonds. And then we're going to do the same thing with our products. So I'm going to have 4x, and then I'm going to have 2 oxygen double bond carbons, and I'm going to have 2x, and I'm going to have 2 oxygen bond hydrogens. And we have to be careful about this one, and this might be the thing that's been throwing you off. If you look on the equation sheet carefully, you'll realize that there are 2 values for carbon-oxygen double bond. There's one that's specific to CO2, and there's one for all of the rest. And that's because CO2 actually has some pretty interesting oxidation states and some pretty interesting energy balancing. And so we get a slightly different value for CO2 than we get for CO, 799. So that 799 is significantly different, at least in terms of, rounding errors, from 745. So we can look at both of those. And we have to make sure that if we've got CO2, we're getting the 799. And then for our oxygen-hydrogen bonds, that's going to be 467. Right? And this is going to be energy that ends up getting released. And I'm really careful, especially in this class, about thinking about it in terms of energy put into break bonds and energy put out from making bonds. Because any of you going on to Chem 125, 128, you're pretty quickly going to get away from considering just bond energy, and you're going to get to bond enthalpies. And then you're going to be taking differences of differences, and so then the order of signs flips for enthalpy calculations. So make sure you pay attention to that. If you're like, I've already done enthalpy and this doesn't make sense to me, think about it specifically in terms of energy to break bonds and energy for making bonds. So, because it's different most of the time we do thermodynamics, we don't think about it just in terms of bond energy like that. So watch out for that in the future. There's another important mistake people make. So let me check. Oh, I just lost track of who I was working with. Tabitha, did you do this calculation and do you know what value you got? Did you use these same numbers?
Yeah, I just did it and I got negative 3279. But I haven't checked if that's right.
I believe you.
It says it's not right still.
Well, hold on.
Okay.
So there's a common mistake that we make. And I think you've made that common mistake, right? So what we've got right now is kilojoules, and I'm going to call this kilojoules per reaction. Not per mole of gas, per reaction. How many moles of gas did you use in this reaction?
Right, we have to divide it by 2.
Yes. So you're going to have one reaction has 2 moles C2H2. So we have to keep in mind that when we do this calculation with all of the molar coefficients like this, we're doing it for an overall reaction. And most of the time when we're doing thermodynamics, we want it in terms of 1 mole of reactant or 1 mole of product. So we can take this number that's per reaction, And we can now say that this is the amount of energy released for 2 moles of ethine combusted, or for 5 moles of O2 combusted, or for 4 moles of CO2 produced, or for 2 moles of H2O produced. So there's actually 4 different ways that we could, that's why it was driving me off the wall. C2H2 also has a special name, we call it acetylene. That's okay. So there's actually 4 different ways we can represent the energy of this reaction in terms of the 4 components in the chemical reaction. Did that work for you?
It still says it's wrong after I divide it by 2.
So let's go ahead. Okay. Hold on, I'm going to pause recording for a moment. Go ahead. So what, you redid your calculation. What was the value you got when you redid the calculation?
After dividing it by 2, or just the...
Before dividing by 2.
I got -2440.
Okay. Also reasonable. So this is one of the things that is probably most frustrating about thermodynamics for me, is we have to be really careful about our, what we call our bookkeeping, right? Keeping track of all of our numbers, because we end up, especially with the way, even though I think this way is more organized, it drives a lot of people up the wall, because you end up with multiple coefficients in multiple parentheses. But for me, it just really helps me keep track of the bonds that make up the materials and how many of each material I have. If we forget one of those multiplications, if you forget this 2 inside here for your OHs in water, you're only counting half of your water bonds, and you get the wrong things. Now, that process should work for number 14, for mastery question set 14, number 4, mastery question 15, set number 2, and question number 2 and question number 3. All 3 of those problems, all 4 of these problems, are really the same process. And once we get this to -2440 kilojoules for every 2 moles of C2, I forgot to write moles. For every 2 moles of C2H2, this really becomes another stoichiometric value. If I multiply by the moles of C2H2 that I reacted, my units of moles will cancel out and I'll just get an energy. Similarly, if I've got an amount of energy that's produced in the reaction, I can figure out how many times the reaction must have occurred for the amount of energy to be released. Energy ends up becoming just another stoichiometric value like the things we were doing last week.
How do you do the second part in it, where it asks about finding the gas and the volume combusted?
So did you get you got your moles of gas from previously correct, right? So you've got 1.27 moles of gas. I'm going to erase these bonds up here for doing this last part. So how do you think you're going to do it?
You know, I'm kind of confused on where to start, to be honest with you.
Okay, well, let's think about what we just had to calculate. What did you just calculate down here with your enthalpy of reaction? Well, let's say this. What was the number you just got right?
-1,220.
What are the units on that -1,220?
kJ mole. Or over mole.
Mole of?
Ethine. C2H2.
So, if this was just 1, how much energy would be released?
That much?
Yeah. What if this was 2?
You divide it, right?
Oh, look at the units.
Multiply.
Yeah, so you're just going to multiply by 2. What if this was 10 moles of gas?
You'd multiply, right?
Yeah.
That's all you're doing. Okay.
Right, so just from the unit analysis, after we have this as a stoichiometric thing, 1.27, you just take this and you do 1.27 times the energy per mole, and you're going to get something that's just a little bit more. You're going to get something that's like 25% bigger than this, because that's about 25% bigger than 1 mole.
Okay, great. Thank you.
Yeah, you bet. So what I want you to do, I'm not gonna do these 3. I'm gonna skip these 3 problems for a little bit. I want you to go ahead and try doing these other ones. Be a little bit more careful in keeping track of your bonds, and see if you can get those. And if you can't, then we'll do them in a little bit. But I'm gonna jump back to looking at the report, the prep, and hopefully when we go through the report, that will also help you with question 6, Mia. Were you able to get the report form, Mia?
No, I was still having problems.
Okay. So hopefully going over the report form will help you with question 6 as well, because they're pretty much identical problems. So it makes sense that if you can't do one, if you're having trouble with one, you'll have trouble with the other. So I'm going to skip these for now. We'll come back to them in a little bit, but let's go ahead and, are there any questions before I erase this? Okay. Let's go ahead and jump to looking at the report form. Now, I always feel like I'm being snide when I ask this question, but I'm also just really curious, and I'm not trying to be snide, but how many of you watched my video on the gas stoich lab and were like, yeah, this makes sense? So what I need to know, and so if you click on participants, you have a little yes, no you can click on. And do me a favor and just, if you watched the gas stoich lab video and it made sense to you, click on yes. And if you watched the gas stoich video and it didn't make sense to you, or if you didn't watch the gas stoich video, click on no. That way it's not that you didn't watch it, maybe it just didn't make sense. So, Jared, did you watch it? You didn't click yes or no, so you said no, okay. So, well, that's not a lot of people responding. I'm going to assume everyone who didn't respond didn't watch it. You know, it doesn't break my heart or anything, but, you know, maybe it does. So, let's go ahead and talk about what's happening in this experiment, because this really doesn't make sense if you don't see the experiment happening. So it might be worth the time to go watch that video, because I walk through this calculation in the video as well. But essentially there's a special experimental setup for how we collect gases, how we measure gases, and that special setup is referred to as an eudometer. It's this long, thin piece of glass. It looks like a burette, except for it's closed on one end. So what happens is we get our eudometer, it's this long piece of glass. We submerge it in, we submerge the open end in a thing of water, and we start with it full of water. Right? And essentially what we have is the atmosphere pushing down on the water outside is essentially making it so the pressure inside here can't push down, right? So the pressure inside the tube is not great enough to overcome the outside pressure. And then we get a gas inside of there, mainly through a chemical reaction. And as that chemical reaction goes, that was bigger than I meant to make it. As that chemical reaction goes, we collect some amount of gas and we overcome some of the pressure. Not all of the pressure, but some of the pressure. right? And so we end up with this empty space. Now, the pressure out here pushing down is equal and opposite to the pressure inside here pushing down. And so the question becomes, what pressure is inside here that's balanced by the pressure outside here? Right, the eudometer is designed just like a burette where there's marks down the side so we can measure the volume really easily. Volume's easy to measure. Temperature, also easy to measure. We just get a thermometer and we're set. Gas constant, given. And then we just have this problem. If we look at our equation again in terms of what we do and don't know, we've got this problem where the N the number of moles of gas in there is kind of the thing we're looking for. That's usually what we're trying to calculate. So that's going to be our thing that's a little bit more complicated. And then the pressure is also a little bit more complicated because there's more than one thing giving rise to the number of moles. So, or sorry, there's more than one thing for the pressure balance. So if I look at this, I want the pressure of H2 times the volume equals the moles of just H2 times the gas constant times temperature. And so to get the pressure of H2, we've got to really take two steps to do that. We have to measure and calculate. And this is what the background of the lab was mostly talking about. Go ahead, click on participants, yes, no, you read the background to the lab. This is just so I know how much detail I need to go into. Mostly yeses, good, okay. So in this case, in the background and also in the lab pal, I believe this is inputted there, we have to recognize that the pressure here is kind of from multiple sources. The atmospheric pressure on the exterior of our tube is balanced by the pressure of the things inside here. The gases that are up there, if there's more than one gas, we'll have more than one gas component providing pressure. And the pressure of the liquid water, right? If you go to the bottom of a swimming pool, you feels like there's a lot of weight on you. That's because water provides, like, from its interaction with gravity, creates some amount of pressure. So we can say our pressure of the atmosphere has at least one component to it, right? At least up there is the pressure from the H2 gas. And this is the first thing that the lab asks us to do. It says, hey, let's just pretend like all of the pressure is just from the H2 gas. What do you calculate for your number of moles of gas produced? And of course, you overestimate how much gas you produced, because the atmospheric pressure is not just balanced by the H2 gas. There's some other components in there. So you say, well, okay, what are the other components that we also need to take into account? Well, we also have to at least consider the pressure of the liquid H2O. And the pressure of the liquid H2O is going to depend on this height. How high is the liquid in the tube above the liquid in the beaker? Because if the liquid in the tube and the liquid in the beaker are at the same level, that means that we're at exactly 1 atmosphere of pressure. But if the liquid in the tube is higher than the liquid in the beaker, that means there's this imbalance between the pressure inside and the pressure outside. And we can figure out how imbalanced that is based on the height of that liquid in that tube. And there's an equation in the background that's specifically designed for the eudometers we have. They have a 1 centimeter, it's a 1 centimeter glass tube with a particular height that's possible. And so the equation in the background will allow us to take into account the correction for the liquid pressure. And then we have to recognize something else. We have to say, okay, well, how many different gases are in the top of the tube? Every gas is going to contribute some amount of pressure. So if we had 6 different gases up there, we'd have 6 different gases providing 6 different pressures. And when we start looking at it in terms of the chemical reaction and what things could be in contact with this, we've got magnesium metal plus HCl aqueous goes to MgCl to aqueous plus H2 gas. And when we look at this and we say, okay, is any magnesium going to become a gas? And in our heads, hopefully you're all going, no, it's a solid, it's a metal. If we're at room temperature, I'm sure at some temperature you can get magnesium to a gas phase, but that's not where we are. Does HCl become a gas? Technically, yes, right? HCl, if it's by itself, is a gas. But at the concentrations we have, it's going to be a very, very tiny amount. And then we can think about, well, why does it have such a concentration? And then we can be like, oh, because water. And when we think about this setup, the other component that is most in contact with our our H2 gas up there is going to be some possibility of H2O being in the gas phase at room temperature. So we have these 3 components that we have to consider in order to figure out just our H2 gas component. So there is an equation in the background for how this height gives rise to some amount of what we call hydrostatic pressure. That's a fancy way of saying water that's not moving. Hydro, water, static, not moving. Water that's not moving creates some amount of pressure. So we can look at the hydrostatic pressure, and that's just going to be based on this height, that stable height above that level. And then we can also say how much water vapor is there at room temperature. So this equation is going to depend on what temperature we're doing our experiment at. Higher temperatures, more water vapor. Lower temperatures, less water vapor. So at this point, it's very much just a matter of plug and chug, right? After we've done this kind of conceptual work, we can isolate our H2 gas. We're just going to subtract these 2 things from our atmospheric pressure, where the atmospheric pressure is measured. Right? We're going to subtract these 2 components from our atmospheric pressure to get our hydrogen gas pressure by itself, and we're just going to plug into the ideal gas law and calculate. And that should give us a way to calculate the number of moles that we experimentally produce. Right? We can do the same thing we did earlier on mastery question on gas questions number 1, and we can just do the stoichiometry from a given amount of metal reacting to find a theoretical amount of H2 gas produced. But to find the actual amount of H2 gas produced, we're going to use our experimental data. How does that do for helping explain things? I'm not sure. There's a few of you stuck on the gas stoic question 6 or the report form part, so I'm not sure how much detail to go into if it's specific number issues. So I just want to do a quick check-in. Does that help? Does that explanation help?
Yeah, that explanation helps me at least.
Okay. Anyone else want to chime in? Tabitha, Mia? Yes, I am. Sorry, someone asked if I was recording this. Yes, I'm recording this.
I just said yeah, it helped.
Okay, good. And then, Mia, did that help you out as well, or?
Yeah, that helped. Thank you.
Okay, so do me a favor, go ahead and try that for the report form. It's the exact same thing for gastoid question 6. So if you're having trouble with gastoid question 6, it makes sense that you're having trouble with the report form or vice versa. But with that thinking, see if you can get the report form to agree or if you can get question 6 to agree. The difference with question 6 is there's a change in the mole ratios. So you have to watch out for the mole ratios in question 6. Okay. So one of the problems that's really challenging in this week's assignment is prep activity the prep activity for the gastoid lab. And it's actually it's straightforward in terms of each step, but it's complicated in that it puts many steps together. But when we break it down into individual pieces, it really is the same type of stoichiometry work we've been doing in the last few weeks. So this thing, I have to open it up and take a look. This experimental idea is actually really important in the way that it's practical. We've got our sodium azide going to sodium metal and N2 gas. Sodium metal is dangerous, so we react the sodium metal with something that will oxidize it, potassium nitrate. That produces potassium oxide, sodium oxide, and N2 gas. These things are still dangerous, but they're less dangerous than sodium metal, which will explode. These things will just burn you instead of exploding on you. So we want to go ahead and react those further. We're going to react the potassium oxide with silicon dioxide. And we're going to react the sodium oxide with silicon dioxide. And these both produce this relatively benign K2O3Si and Na2O3Si. And these things are really not very reactive. And the question is, and I'm going through this pretty quickly because the people in office hours today say they watched the video yesterday, they watched Dr. Ness' video, and they're just having trouble with some of the number ideas. So the idea here is the amount of sodium produced here is going to be the amount that reacts here. And then the amount of K2O that's produced here is going to be the amount that reacts there. So we've got a coupled series of reactions. And while we can do the stoichiometry for each reaction separately, is really thinking about how they all together create some process. And then this Na2O is going to be reacting there. And one of the things that throws people off is what our starting material is. So we start with 50 grams of sodium azide. We start with 50 grams of KNO3. And we start with 50 grams of SiO2. And that means that these two reactions are going to have a common reactant between them, and that's going to create a spot where a lot of people have trouble. So I'm going to kind of work specifically with somebody's numbers to see how they're doing. And I think it was Mia, you wanted to look at this, right?
Yes, please.
Okay, so I need to get some numbers from you to figure out where things are going right and where things are going wrong. How many moles of sodium azide did you calculate from your 50 grams?
0.769.
That sounds good. What was your mole rate? What was your balancing coefficients for this first reaction?
2 moles of Na and 2 moles of Na, and 3 moles of N2.
Okay. So how many moles of sodium did you have made over here?
0.769.
Perfect, right? It's a 2-2-2 ratio, that's fine. So then you brought your 0.769 down here. Right? I put 50 sub 3 instead of 50G. What were your balancing coefficients for this second reaction?
10 Na, 2 KNO3, 1 K2O, 5 Na2O, and 1
That looks good. That's what I was expecting. So how many what were your number of moles of K2O produced?
I got, okay, well, maybe this is where I'm confused because I used the ratio, like I multiplied the 0.769 by 5 because I thought, because it was 10 Na, because before it was 2 Na. Is that incorrect?
No. So after we've done this reaction and we've got this amount, we're going to bring it down. And this is now a separate reaction happening, following a different recipe.
Okay, then that's definitely where I went wrong.
That's where you went wrong. So this should be a 10-to-1 ratio, and this should be 0.0769.
Okay.
And that's probably where you're going wrong. So the other place, so it is one of those things where when reactions happen in a series like this, it really is like following several different recipes where, this recipe and this recipe don't affect each other besides the fact that one thing you made is then being used in your next recipe. Right? It doesn't matter. I like to think about it in terms of making cakes. It doesn't matter how you made the frosting, it just matters how much frosting you have after it's made. I don't know if that analogy helps or not, but now I want cake. The other place where people get in trouble or get confused or miss something important is our SiO2 is going to be reacting twice. So you're going to have 50 grams minus the amount that reacts with K2O and minus the amount that reacts with Na2O. So you're going to have 50 minus first reaction, then minus second reaction. That's another important thing people miss. Okay. Is it okay if I let you keep working on that for a little bit?
Yeah, thank you. I'll go back to the question.
In the meantime, I'm going to go ahead and hop over to mastery question 15. Oh, hey. Ta-da! Here's exactly what I was talking about. So I'll leave this board as it is, and I'll erase this board. Sorry. That was funny. So Ashley, I didn't just erase it. It's on the other side of the board. In any case, let's look at mastery question 15. I'm just going to do number 3 and see if this works for kind of explaining the other things. Well, let me ask. Mastery, and I think Tabitha is going to have a strong opinion about this. Mastery question set 14 number 4 or mastery question set 15 number 3?
15 number 3 would be good for me.
40. Oh, so we got a split. Some people want 14.4, some people want 15.3. I'll start with 15.3 and then I'll go do 14.4 if we need to. And for 14, if we can do 15.3, 14.4, maybe we just need to look at the setup of that together. So.
I was able to do all of MQ15, but I still can't get MQ14 number 4.
Okay, well, maybe I should double check that one and make sure there's not a typo in it too. So, mastery question 15.3. Whoa, what? Oh, is calculate the enthalpy of photosynthesis. How much fun. So this is the process that plants use to make cellulose and glucose and other things. We're looking at the construction of glucose. So we're going to be doing something that is energetically unfavorable. We're going to have CO2 plus H2O forms C6H12O6 plus O2. We're going to use the bond enthalpies in the equation sheet. And there's something about the reaction that produces 3.7 moles of glucose. And we want to figure out the energy in kilojoules for a certain amount of this happening. So first thing we have to do is, of course, balance the chemical equation. I'm going to want 6 carbons. So I'm going to have a 6 there. 12 hydrogens. So I'm going to have a 6 there. And that's going to give me 6 oxygens and then a 6 there. Right, 6 of my oxygens are there. And then 12 more of my oxygens are there. So it's 6, 6, 1, 6 for my balancing coefficients. That's fine, that's going to be important. The next thing that's going to be really important is keeping track of our structures. So I always like to, when I'm doing this, actually draw the structures so I can keep track of which bonds I'm breaking and which bonds I'm forming. And I'm going to want 6 of those CO2s, and I'm going to want 6 of those H2Os. And then I'm going to have to actually look up the structure for glucose to make sure I don't mess anything up. And Lewis structure for glucose is going to be something like that. Let me make sure I got this right. 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 oxygens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wait, where am I missing? Oh, let me count my hydrogens again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, 12. That's the one I'm missing. So I'm going to write this structure, even though that should be enough. I'm going to write down the structure a little bit more explicitly to make sure I don't forget any of my carbons or hydrogens or oxygen bonds. So I'm going to have a carbon to an oxygen to a carbon to a carbon, a hydrogen, and another carbon. This carbon is going to have 2 hydrogens on it, and then an oxygen with a hydrogen on it. Wow, we picked a really complicated one for doing this. But here we go. It's too late. We're doing it. To an oxygen with a hydrogen, another carbon, oxygen, hydrogen, another carbon, another hydrogen, an oxygen, a hydrogen. Wait, did I mess this up? 1, 2, 3, 4, 5. Oh, there we go. To another hydrogen, to an oxygen, a hydrogen, another hydrogen. And now I've got to make sure I've got everything again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep, I'm good. Okay. So what a little mess for getting this. So chances are that we just missed, if we're having trouble with this, maybe we missed a bond someplace. And we're going to have just one of those, and then we're going to have 6 oxygen-oxygen bonds. And right now this is kind of a mess. So I'm going to first take apart this thing and figure out what I've got to deal with. So I'm going to have one of these, which is going to have, first I'm going to keep track of all of my carbon-carbon bonds. So that's 1, 2, 3, 4, 5 carbon-carbon single bonds. So I'm going to have 5 times a carbon-carbon single bond. Then I'm going to go through and I'm going to find all of my carbon-oxygen single bonds. It's 1, 2, 3, 4, 5, 6, 7 carbon-oxygen single bonds. Oh, 1, 2, 3, 4, 5, 6, 7. I didn't give myself enough space. 7 carbon-oxygen single bonds. Then I'm going to go through and check all of my oxygen-hydrogen bonds. It's going to be 1, 2, 3, 4, 5. I'm going to have 5 times oxygen-hydrogen bond. And then I'm going to count all of my carbon-hydrogen bonds. I think that's going to be, well, no, 1, 2, 3, 4, 5, 6, and that's going to be 6 carbon-hydrogen bonds. That should get me this entire structure, assuming I didn't forget anything. I think that's all of them. Every line has a dot next to it, right? Yes. Okay. And it's nice to have, I like to have multicolored pens around when I'm doing these types of things because this is actually how I keep track of things so I don't miss anything. After I've done all of my bookkeeping and I'm sure I've got it right, I can go ahead and just release that. And all that really matters is which bonds we are forming. So I'm forming 5 new carbon-carbon bonds, 7 carbon-oxygen bonds, 5 oxygen-hydrogen bonds, and 6 carbon-hydrogen bonds. I'm going to be forming and 6 oxygen-oxygen bonds. I'm also going to be breaking, let's do the same thing over here for our reactants. So every CO2 is going to have 2 carbon-oxygen double bonds. And every H2O is going to have 2 oxygen-hydrogen bonds. And now, after I've done all of that bookkeeping, it's really just a matter of identifying the correct bond energies and doing some algebra. So, equation sheet handy. Don't laugh at me, Jerry. You're laughing at me. We're going to go ahead and plug in our different values. Straight off of this, carbon-carbon bond is 347. Carbon-oxygen single bond is 358. Oxygen-hydrogen single bond is 467. And a carbon-hydrogen single bond is 413. Oxygen-oxygen double bond is 498. Oxygen-hydrogen single bond is going to be the same value we had before, 467. And this is where we have to be careful. Carbon-oxygen double bond has 2 values associated with it. It has a value that it generally has of 745, and then it also has the value that's particular to it in CO2, and we want to use that value of what's particular in CO2. We also have to recognize that this is bonds breaking. That's where we're going to be putting energy in. This is going to be bonds forming. That's going to be energy out. So we're going to do the bonds that we break minus the bonds that we form. And this is different, and we have to be careful. For those of you that are going on to 125 or 128, you're going to very quickly get to enthalpy calculations where you're going to be calculating a difference of a difference. So your sign is going to flip because you're going to be doing a difference of a difference. Here we're just doing a difference. So Make sure you pay attention to that in the future. But for us right now, we're just going to do this calculation. So do me a favor, those of you with calculators, calculate. Take the amount of energy in the bonds that we're breaking, subtract it from it the amount of energy from the bonds that we're forming, and let's get the energy of a reaction.
So for the long one, it's 9,054
Just
kilojoules per mole.
for just this, not without the 602?
And then with the 6 oxygens, it's 12,042.
Oh, 12,042.
Yeah, 12,042.
Okay. Do me a favor, those the rest of you who are in here at office hours, make sure Jared's using his calculator correctly. Not that I don't trust him. It's just the scientist in me. You know, you always want to have multiple confirmations. Tabitha agrees with you, Jared.
I agree.
What about the energy from the bonds that we're breaking? 12 times 799 plus 12 times 467. I can't do that in my head, I'm sorry. My calculator's all the way over there.
7,596. Oh wait, no, sorry, times 2. Each. So it'd be 15,192.
How much?
15,192.
Okay, that's more what I was expecting. I got worried. I was like, this is supposed to be endothermic. Okay, Tabitha agrees with you again. So what we can do is we can do this number minus that number, and we're going to get an amount of kilojoules. 3,150?
Your head's in the way of the,
sorry.
of the number. Yeah, you're good.
And the thing that a lot of people forget is I would call this kilojoules per one reaction. Right? So if I did this reaction once, and doing this reaction once requires 6 moles of CO2, 6 moles of H2O, and gets us 1 mole of C6H12O6 glucose. That would require us to put in 3,150 kilojoules of energy, because it's a positive number, endothermic. So when I look at the problem, it's now asking us to estimate the enthalpy change of the reaction that produces 3.7 moles of glucose, which, since each reaction produces 1 mole of glucose, well, this is saying, well, what happens if you do the reaction 3.7 times? Or whatever number you have. Right, so this number of 3,150 kilojoules, one reaction, I could do one reaction is 6 moles of CO2, one reaction is 6 moles of H2O, one reaction used, or one reaction is 1 mole of glucose produced, or one reaction is 6 moles of O2 produced.
That's still not giving me the correct answer. Like once I multiply out the number of moles, it still says it's not correct for me.
Did you make sure that Jared did his calculation correctly?
Yeah, I did it with him as well.
Yeah.
Okay.
I confirmed both those numbers as well as.
Let me do a quick check. We found my mistake. The reason people aren't getting the right answer is because I made a mistake up here someplace. I didn't count right. Should I say what so everyone who's in office hours knows what the mistake is. Should I tell people at home what the mistake is, who are watching this later, or should we make them figure it out?
Are they aware that there's a mistake?
Well, I just told them I'm recording now, so they know there's a mistake, and they know that everyone who's in office hours is deciding whether we give them the answer or not. How about this? I'll tell you where my mistake is, but oh no, it disappeared. I'll tell you where the mistake is, but I won't tell you how to fix it. The mistake was I miscounted my CH bonds in my glucose. So this is not supposed to be a 6. I'm not going to tell you what it's supposed to be, but everyone in office hours just fixed that and got the right answer, and it worked out. So double check, go through. That means that this number is going to be off by a little bit as well. So go through and make that correction. And I'll make it even more dramatic by putting a bright question mark there and a squiggle question mark there. So go back, recalculate those. The process was all correct except for I miscounted by 1. So that will get you that mastery question. But people are still having trouble with mastery question 4. Mastery question set 14, number 4. So we're going to go ahead and take a look at that real quick. Oh, and I just realized office hours are over, but I'm going to keep going anyway. Oh, great. Glad to hear it, Tabitha. Did you figure out number 4 as well?
Yeah, I got that one.
Awesome. Okay. So was it just a matter of being careful with your counting, same kind of thing I did here?
Yeah, I just wasn't doing it right, where basically, yeah, you just multiply it by the limiting moles after, which I didn't realize that.
So the thing that we have to keep in mind is kilojoules per reaction when we do these calculations. So if you are looking at a situation, so the thing that's throwing a lot of people off on set 14, number 4, is the fact that we also have to take into account the limiting reactant. And the limiting reactant is going to determine how many times we can complete the reaction. So when we consider how many times we complete the reaction, we're going to be using just the moles of limiting reactant for that.